Welcome to the GCSE Combined Science Trilogy Higher, Paper 2. Okay, the Sun emits a continuous spectrum of electromagnetic waves. Figure 1 names some of the groups of the waves in the electromagnetic spectrum, but it's missing a few. It is asking us to name groups A, B, and C in Figure 1. Some people have different mnemonics for remembering the order of the electromagnetic spectrum. Whatever your method of remembering is, you use that. But for some people it's red Martians invade Venus using X-ray guns. Okay, and then they get the order of the electromagnetic spectrum. Whatever it is, this is the order that you have to come up with. Radio waves, infrared, ultraviolet, visible light. Infrared, visible light, ultraviolet, X-rays, and gamma rays. Okay, so what are we missing? R is for radio waves. M is for microwaves. And C is for X-rays. There we go, we've done those three. Give one similarity and one difference between the properties of ultraviolet waves and gamma rays. So what are some of the similarities between ultraviolet waves and gamma rays? They're both part of the electromagnetic spectrum, so they travel at the same speed in a vacuum. Vacuum is one of the only, well, it's the only word I know with two U's consecutively. They both transfer energy. And they are both transverse waves. But the differences are gamma rays has a higher frequency or a shorter wavelength. Wavelength, okay, and gamma is more ionizing. And more penetrating. Okay, penetrating. Okay. Figure 2 shows white light split into a spectrum of different colors by a glass prism. White light goes in and is split up into the colors of the rainbow. This process is called dispersion. But what causes dispersion? It's the fact that all of the wavelengths of light, they refract a different amount when it goes through the prism. So light changes direction when it enters a glass prism. What is the name given to the process where light changes direction? Is called refraction. Use the physics equation sheet to answer the questions in 1.4 and 1.5. Write down the equation that links frequency, wavelength, and wave speed. Frequency, wavelength, and wave speed is linked by the equation that V is equal to F lambda, or wave speed is equal to frequency times by wavelength. Things to remember here are that wave speed is measured in meters per second, just like any other speed. Frequency is measured in hertz, and wavelength is measured in meters. The wave in the middle of the spectrum has a wavelength of that much meters, 5.0 times 10 to the minus 7. So that's a small number. The wave speed of light is 3 times 10 to the 8 meters per second. That's a big number. Well, how do I know? Well, this has a minus 7, so the decimal point moves to the left 7 times. This has a times 10 to the power of 8, a positive 8, which means the decimal point moves to the right 8 times. Calculate the frequency of the wave. Thankfully, the good thing is I can use the same numbers without changing anything and put it into my calculator. If you don't know how to do that, the numbers that you would put in are now 0.00000005, which means, if I'm correct, the decimal point has moved 1, 2, 3, 4, 5, 6, 7 times. Okay, and this number will be 3,000,000,000,000, and the decimal point has moved 8 times. However, we don't need to do any of that. We can just put it into our calculator to find frequency. Let's rewrite the equation first. V equals F times lambda, and lambda is the wavelength, it says here, and V is the wave speed, which is here, and frequency is what we're trying to find out. So I will rewrite the equation and put the numbers in. 3 times 10 to the 8 is equal to frequency times by 5 times 10 to the minus 7. Rearrange the equation to make frequency the subject. Now, how would you do that? This whole thing is timesing onto frequency. So to remove it from this side, I'll divide 5 times 10 to the minus 7 from this side, which means I have to divide 5 times 10 to the minus 7 from this side. Now, if you do not know how to rearrange an equation, you need to put a lot of practice into it, because a higher paper will require you to do a lot of it. So once we've rearranged it, what we notice is, well, 5 times 10 to the minus 7 divided by 5 times 10 to the minus 7, well, these two cancel each other out, and you're left with frequency is equal to 3 times 10 to the 8 divided by 5 times 10 to the minus 7. Here we have a very large number being divided by a very small number. I can imagine the frequency to be a very large number. Okay, the frequency is 6 times 10 to the 14 hertz, and double underline, that should be on an answer line. It's cut out. A student investigated how the acceleration of a trolley is affected by the force acting on the trolley. Figure 3 shows some of the equipment used. Trolley, runway, table. Describe the method the student could use. You should include any extra equipment needed. This is a tricky practical, so you have to listen very, very closely, because there's a lot of things that can be done in many different ways. I'm going to first start by highlighting what my variables are. I've got my acceleration, which is being measured, which is my dependent variable. Remember, don't mess in class, stay calm. Dependent, you measure. The thing that's being measured or being investigated for is my acceleration. The trolley, and affected by my force. That's my independent variable. Independent, you change. So that's the variable that I'm varying. Then we haven't been told any of the control variables, but we're going to get there. How are we going to vary the force on the trolley? There's 3 ways that I'm going to talk to you about. And one of those ways is silly. We could vary the force on the trolley by saying, I'm going to push the trolley along. If I'm going to push this trolley, here's the trolley, along, I'm going to have to push it constantly, but there's no way to determine whether my pushing is a constant force throughout the journey of the trolley. I know I can vary the force because I can push harder or slower, or harder or lighter, but there's no way that I could actually measure what the force from my hand is. Another way is saying, well, the trolley's already on a ramp. I could change the height of the ramp. If I change the height of the ramp, then the direction or the vector of the force of the weight acting on the trolley down the ramp increases. Now all of the weight is acting down. Now some of the weight is acting down, but because the trolley is on a ramp, it is experiencing a force down the ramp. That is going to change my acceleration. We could measure that because using maths, obviously, you can see how much of the force is acting down, or you could use a force meter to see how much the trolley is trying to pull down the ramp. That's doable. Or you could use the best method, which is by having some slotted masses hanging off the bench that will pull on the trolley using a string, and the string has to go over a pulley. So one of the first equipment that I'm going to add is a pulley, and I'm going to have a string going from the trolley over the pulley onto a set of slotted masses. I'm going to do the slotted masses in a slightly different color. And this is the mass hanger, so that's holding them. So here is the setup that I've got. Now I have to establish a few things. The weight of the slotted masses is the force that is pulling the trolley. The weight of the slotted masses is the force that is pulling the trolley. So if you imagine there are 10 gram slotted masses all adding up to 100 grams, then there's 100 grams times by gravity, which is the weight, that much force acting on the trolley. What's 100 grams times by gravity? Well, it has to be in kilograms to do it anyway. So weight equals mass times gravity. 100 grams is 0.1 kilograms times by 9.8 gets me 0.98, which is almost 1 Newton of force. Then I can take one slotted mass off, because then it would be 0.9 newtons, then another Newton off, which is going to be 0.8 newtons, and so on and so on. So my independent variable is the force, and how I'm going to vary the force is varying the mass on the mass hanger varies the force on the trolley, because weight of mass hanger is equal to force. Weight is equal to mass times by gravity. That's it. So that's what we're going to do. Then we have to measure the acceleration. That's my dependent variable. This takes a little bit more effort. Acceleration. Make sure I don't spell it wrong. And I'm going to make spelling mistakes because I'm writing so fast. So, to measure the acceleration, you can mark out on the trolley, on the ramp, 20 centimeters intervals using a meter ruler. Then using a stopwatch, measure how long it takes to move through each 20-second intervals, or the 1 meter interval, depending on how lazy you want to be. And you will have a distance and a time taken to cover that distance. Okay, so mark the distance traveled by the trolley using a rule, using a meter rule. Then use a stopwatch to time how long it takes for the trolley to move this distance. And what we recognize is velocity is equal to distance, which is marked by s, remember, divided by time taken. Acceleration is therefore equal to change in velocity divided by time taken. Both of those equations used together can find the acceleration. But the better way of doing this, and this is the way that I prefer you would put it in, right? The better way of doing this is, of course, use light gates. And what do light gates do? Well, a light gate would attach a card onto the trolley, and two light gates, or maybe one light gate is enough if the trolley's distance is measured, or two light gates if we're putting it at the beginning and the end. Okay, and when the trolley goes through the light gate, it measures how long it takes, or it measures the velocity of the trolley at that point. And it would use some maths, exactly the same maths as we were going to do manually, to measure the acceleration of the trolley. So it uses light gates, and I'm going to have to consult the mark scheme to see what the mark scheme says specifically. It uses light gates to determine time or speed. Computer calculates acceleration. Use light gates to determine time or speed. Use a computer to calculate acceleration. Okay, so we've calculated the acceleration. There's other ways of calculating acceleration that you can look at, and pretty much every single video on YouTube of how this practical is done in a slightly different way. If I were to do this practical, I would sack off the v equals s over t and a equals change in velocity over time, and I would introduce a new equation, but you don't know that equation, so we're not going to delve into that. That would only bring confusion. We've done the independent variable. Okay, we've done the dependent variable, dependent, independent. We need to do the control variables. Before we do the control variables, I want to mention that this would give us around 4 marks. To get it to the 5 and 6, we need to tick off everything that they've asked us to do. We've described a method, but have we listed any extra equipment? We've drawn it out, but we haven't listed it. So let's talk about it. Attach pulley to bench. I don't know whether just saying set it up exactly how we've drawn it is good enough, because this is a pulley and anyone can see that it's attached to the bench. Attach string to trolley and put it over the pulley. That's also very, very obvious. This is the slotted masses. Mass on hanger. Okay, and then attach mass hanger on the end of the string. This is what produces the acceleration. Finally, the control variable. This is I'm going to take time with. Control variable. How awesome that this isn't even mentioned in the mark scheme, but for me it makes logical sense to talk about the independent, dependent and control variable of an investigation like this, especially seeing as this investigation is so complicated. So what is the one thing that we're trying to control? That it seems from the investigation, from the independent variable and how we varied the independent variable, it seems that we don't control. It's the mass of the actual whole system. What is the system? Everything that is inside this orange bracket is one single system. If I take the slotted mass off the mass hanger and put it at the side, then I am removing it from the system. The mass of the whole system is the mass of the trolley added to the mass of the mass hanger. So how would we control it? Well, every time I remove a slotted mass from the mass hanger, I should put it onto the trolley. Every time I remove one mass from here, I should put it here. That's it. So, control the mass of the system by placing the removed slotted mass onto the trolley. Thank you for listening for all this time to answer your 6 markers. But if you follow the logical steps that we've been set out here, it's going to go smoothly. Table 1 shows one set of results for a similar investigation, resultant force in newtons, acceleration in meters per second. The question is, which of Newton's laws predicts that the acceleration of the trolley is proportional to the resultant force of the trolley? Let's see. Newton's first law says that an object in motion will stay in motion, or an object at rest will stay at rest unless acted on by a resultant force. Does that say resultant force is proportional to acceleration? No. Newton's third law says that if I apply a force, I experience an equal and opposite force back. So it's not that. So it's Newton's second law. Newton's second law says force is mass times acceleration. In other words, the acceleration of an object is proportional to the force acting on the object. Determine the acceleration of the trolley when the resultant force is 3.6 newtons. Use table 1. That's really interesting because we've been given the force, we've been asked to calculate the acceleration. We know the equation is force equals mass times acceleration. However, we haven't been given the mass. How very confusing. But it says use table 1. In table 1, it says that is the force, that is the acceleration. Force equals mass times acceleration, remember. And we could calculate the mass from these two numbers. But they don't say use the physics equation sheet. Often when they ask you to write down or do a calculation, they will say use a physics equation sheet. Instead they say use the table. This is where the whole question has to be read together. It already tells you that acceleration of the trolley is proportional to the resultant force. That means if I double the force, I double the acceleration. If I triple the force, I triple the acceleration. What have I done to the force from table 1 to question 2.3? In table 1, the force was 1.2. In question 2.3, the force is 3.6. What have I done to it? I have tripled it, times it by 3. That means if acceleration is proportional in the same way, in table 1, it is 1.6. In question 2.3, for our answer, we also have to times it by 3. 1.6 times by 3 is equal to 4.8 meters per second squared. That's one way of doing it. The other way of doing it, and by the way, everything in the green brackets has to be included for those working out. The other way of doing it is what we mentioned before. We could find the mass of it. We could say that 1.2 is equal to mass times acceleration, which is 1.6, of course. And therefore mass is equal to 1.2 divided by 1.6, which is 0.75. And then use that 0.75 here. 3.6 is equal to 0.75 times by acceleration. Therefore acceleration is equal to 3.6 divided by 0.75, which happens to be 4.8 meters per second squared. I've used both methods. Same answer. Use the physics equation sheet to answer questions 2.4 and 2.5. This time they are telling us to use the equation. acceleration, mass and force F equals ma. Resultant force of 0.42 newtons acts on a different trolley. Calculate the acceleration. That's my force. That's my, the acceleration is given, and calculate the mass. 0.42 is equal to mass times by 1.2. Mass is equal to 0.42 divided by 1.2. Gives you an answer of 0.35 kilograms. The teacher used a ripple tank to demonstrate water waves. The teacher used a lamp to project the shadow of the water waves onto a screen below the ripple tank. Figure 4 represents the shadow of the water waves seen on the screen. 1 millimeter on figure 4 represents 5 millimeters on the screen. So, determine the accurate value for the wavelength of the waves on the screen. Here is our scale, and 1 millimeter here equals 5 millimeters on the screen, and we have to measure the wavelength on the screen. When you see multiple waves and you're asked to find the wavelength, you look at the number of full waves and you measure the length of the number of full waves, and then you divide by the number of waves so that you have the length of one wave. So in the same way, you have to measure the length of the number of full waves that you see and then divide by the number of waves that you see, but you must also times that number by 5 to convert it from 1 millimeter scale to 5 millimeter scale. You can't, well, I can't do this measurement on the PowerPoint because the scale that I have, because I've screenshotted it and I've put it onto the screen, it's not going to be the same. Even if I use my ruler to put it on, it's just not going to read the same value. But the answer should be from here all the way to here, the distance across all 8 wavelengths should be 113 millimeters. And why do I say all 8? Well, from here to here is 1. This is 2, 3, 4, 5, 6, 7, 8. 8 wavelengths. So from each of the shadows, you could imagine that as the trough or the peak of the wave. You count from the same point each time and you find that there's 8 waves here. So 8 wavelengths equals 113 millimeters. Well, timesing that number by 5, because 113 millimeters times by 5, 113 times by 5 gets you a bigger number. 113 divided by 5 gets you times by 5 even. 565. And 565 is the distance of all 8 waves on the screen divided by 8 gets you the distance of one wave, which happens to be 70 point something 6 millimeters. Okay, so an answer from, now because people measure it not perfectly, that you're meant to measure it right from the middle, because people might not measure it perfectly, you might get a discrepancy, a range of answers from 68 millimeters all the way to 72 millimeters. Somewhere around 70 millimeters should give you the right marks. The teacher adjusted the frequency of the waves produced in the ripple tank. The teacher measured the wavelength 5 times. Table 2 shows the results. Calculate value x in table 2. So here's measurement 1, 2, 3, 4 and 5. Then they've calculated the mean. You have to calculate the value of x, so you have to find what the missing value is. So how do we calculate mean? How did they calculate this value? they did 96 plus 99 plus 97 plus x plus 97 equals, all divided by 1, 2, 3, 4, 5, 5 equals 97. That's the calculation that they did to get to 97. You just have to do the reverse. So if this side is being divided by 5, times this side by 5, and times this side by 5, these two cancel out. So this side becomes, on the right hand side, becomes 97 times by 5, which is 485, is equal to, and then you add up the terms that are just numbers, which is 96 plus 99 plus 97 plus 97, and obviously plus x, but we can't do that. It ends up being 389 plus x. Then you do some rearranging to find that x is equal to 485 minus 389, and your answer is 96 millimeters. The teacher states that the results are very precise. Which of the following supports the statement made by the teacher? The mean value is very close to the true value. The spread of the values is about the mean is very small. The values are all given to the nearest millimeter, and the wavelength measurement was taken 5 times. Well, we can discount these two, but we are unsure about the first two answers. So let's see. Here is a dartboard, or like a target, with the red bit in the middle. Now, when you shoot your arrows at it, if all of the arrows end up right here, then we say that is very precise. However, it's not very accurate, because for it to be accurate, it needs to be here. Okay, so in the same way, if the spread of the values is small, just like this, it's very precise. However, if the value is close to the true value, it's accurate. Describe the difference between longitudinal waves and transverse waves. This is a simple definition. In longitudinal, the waves, the oscillations, are parallel to the direction of energy transfer. Whereas for transverse, the oscillations, which means vibrations by the way, are perpendicular, which means right angles, to the direction of energy transfer. Okay. A teacher demonstrated the motor effect. Figure 5 shows the equipment used. The equipment includes a permanent magnet. The copper rod remains stationary while the switch is open. Complete the sentence. The tendency for an object to remain stationary is called inertia. Inertia is to do with the mass of an object, and to get it to move, you need to overcome the inertia of that object. Something that's big has more inertia. When the switch is closed, the copper rod accelerates. Which direction will the copper rod accelerate? To answer that question, we need a diagram. And in this diagram, we see that there's the magnetic, the permanent magnet, which causes the magnetic field to go down. So here's the magnetic field in blue. Okay, so I'm going to put that as F. Okay, and then there's the current, and I'm going to use the red color for the current, and the current flows from positive to negative. So if we look, it starts here, goes this way, this way, this way, and the current in the rod is going from that side out of the page, sort of this way, back round, and so on. when the switch is closed, obviously. Okay, so the red is the current, and finally what we're asked is the motion, which way it will move. And to do that we need Fleming's left-hand rule. You can notice that I've put F on my first finger, that represents the field. I put C on my second finger, that represents the current, and I've put M on my thumb, which represents the motion. So now I don't condone scribbling on yourself. However, this is just to demonstrate to you how the left-hand rule works. What we must do then, and it might not work because I'm doing it to the camera, and it might be the opposite way around for you. What we will do first is make the field, the first finger, face the direction of the field. Field always goes from north to south. Then, obviously, the second finger, we face the direction of the current, and the current is coming out of the page. And because these are perpendicular to each other and these are perpendicular to each other, see, all three fingers are at right angles to each other, what we find is the thumb, it faces to the right, okay, and therefore the motion of that rod will be to the right. It will have a tendency to move that way because the current is that way and the field is that way. Next question. Explain one way the teacher could increase the acceleration of the copper rod. For any of these questions that talk about electromagnetism, when they ask you to increase one thing, remember they're asking you to increase the acceleration, the motion. What we can control is these two things, the field and the current. So one way is increase the current. Okay, and that would increase therefore so it will have a greater force or resultant force. Then another way is to increase the strength of the field. To increase the strength of the magnetic field, we can use a stronger magnet, and when we use a stronger magnet, the explanation bit will be so it will have a greater force. The magnet used in the demonstration was a permanent magnet. Figure 6 shows an iron bar and a permanent magnet. Describe how the permanent magnet could be used to test if the iron bar is also a permanent magnet. So here's the thing. If the iron bar is a permanent magnet, what will it have? It will have a north and a south pole. Let's say, for example, that this is the north and this is the south pole of this iron bar, this permanent magnet, which is obviously just an iron bar. What will happen if I bring the north pole and the south pole together? Well, they will attract, okay, and that doesn't tell us anything. Okay, see, a magnet and another magnet will attract, but a magnet will attract a magnetic material. So the attraction doesn't tell us anything. What we'll be telling is, if one side attracts and we turn it around, the other side should repel. Because if we turn it around and we face the south poles to each other, they should repel. And that's how we know if this iron bar is a permanent magnet. Just to answer the question in the exam language, they have said, bring the iron bar close to the pole out of the permanent magnet. If any side repels, then it shows the iron bar is a permanent magnet. So bring the magnet close to the iron bar. If there is repulsion, then it is a permanent magnet. Next one. Figure 7 shows a magnetic compass used by walkers. The question is, explain how a magnetic compass provides evidence that the Earth has a magnetic field. So, you'll have seen compasses before in your lesson when we learned about magnetism. When we hold the compass in our hand, what happens is the compass itself is a permanent magnet with one side painted red, or it might have an arrow on one side, and that arrow, which would be the south pole of that magnet, would be the south pole of that magnet, would line up and face the magnetic north pole of the Earth. And weirdly enough, the magnetic north pole of the Earth is actually the south pole of the Earth, but that's for a different discussion. So what will happen is the compass needle will point in the same direction always because it's an explained question, because it aligns itself with the Earth's magnetic field. Now, if the Earth didn't have a magnetic field, it wouldn't align itself. The graph shows, the figure 8 shows a garden chair hanging from a spring. Which of the following describes the relationship between weight acting on the spring and the extension of the spring? Weight and extension are directly proportional to each other, because what we have to imagine is weight is the force that is acting on the spring, and force is equal to spring constant times by extension. Therefore, we know that force and extension are directly proportional, and this is the symbol, so here it is. The person in figure 8 has a weight of 750 newtons. The person's weight causes the spring to extend by 60 millimeters. Okay, I'm already thinking millimeters is not the right standard unit. Calculate the spring constant of the spring. Use the physics equation sheet. Now, just to remind you, the equation that we need is force is equal to spring constant times by extension. However, before we move on, we need to convert the extension. Extension is equal to 60 millimeters, which is equal to 60 times by 10 to the minus 3, or divide by 1000 to get to 0.06 meters. So now that we know that, and we know that that is the force, we can do 750 is equal to spring constant times by 0.06. Therefore, spring constant is equal to 750 divided by 0.06. Now, if you want to know how we got here, and I know everyone's doing higher, so it should be easy enough for you. You have to divide this side by 0.06 to get rid of it, to get k on its own, or we say to make the k the subject of the equation, and that means those two things can cancel out. But if you do that onto one side, you have to do it onto this side, and now that every term next to k cancels out, you can see that k is equal to 750 divided by 0.06. And finally, you just write down what the answer is, which happens to be 12,500 Newton meters. Okay. The manufacturer of the chair tests a new spring to see if it's suitable to hang the chair. The spring can store a maximum of 1,800 joules of elastic potential energy before it becomes inelastically deformed. Describe what is meant by inelastically deformed. So after that much energy, what happens to that spring is you can stretch the spring and it won't spring back to its original shape. What's a characteristic of an elastic band? That you can stretch it, and when you let it go, it flings back into its original length and shape. That's what an elastic band does. So an inelastic deformation is when the force is removed, but the spring does not return to its original length. That's inelastic deformation. And this spring can store a maximum of 1,800 joules before being inelastically deformed. If you put 1,801 joules, it won't return to its original shape. Calculate the maximum extension of the spring before it becomes inelastically deformed. Remember, the maximum energy that you can put in, elastic potential energy, is 1,800 joules. So here we have the energy, and then we're asked to find the extension. The equation that links energy stored in a spring and the extension is this equation, E equals half KE squared, where the little e is the extension. And I'm going to underline this little e because that's what we're trying to find. So, elastic potential energy, 1,800 is equal to half times by spring constant, which is given as 225, times by extension squared. And then to find, to make extension the subject of the equation, what I might have to do is I'll have to do whatever's being done onto the right hand side, I'll have to do the opposite onto both sides so I can just get E on its own. So just very easily, it's been times by 225, so I have to divide by 225. It's been times by a half, so I have to divide by a half. And E is being squared, so I have to square root it. But I'll do it step by step. E squared is equal to 1,800 divided by a half times 225. I'll put that in brackets. And the last step is E is equal to square root of 1,800 divided by a half times 225. Notice how I made my square root sign very big, because I just want you to know that this whole thing, after you compute it, is being square rooted. When that is done, the extension happens to be 4 meters. So, what's the issue here? Well, the next question asks, evaluate the suitability of the new spring to hang the chair. The maximum elastic potential energy is that, yeah, we know, spring constant, the weight of the person is 750 newtons, and the distance between the bottom of the chair and the ground is 30 centimeters. So if that chair moves 30 centimeters or more, then what you have to say is that this spring is useless. Okay, so if that person sits, will that chair move 30 centimeters? How do we know? Force is equal to spring constant times by extension. And if we can find the extension that we will cause when a force of 750 newtons is used on the spring, which has a spring constant of 225 newton meters. So 750 is equal to 225 times by E. Therefore, E is equal to 750 divided by 225, which is 3.3 something meters. Now, if the spring extends by 3.3 meters when a person with a weight of 750 newtons sits on it, then this spring is unsuitable for the application of hanging the chair, because what's going to happen is 3.3 meters is greater than our 30 centimeters, which is exactly the same as 0.3 meters. Therefore, so I'm going to say extension is too great, too large, so not suitable for chair. And that's the calculation that we're doing. Now, obviously, we can go a different way. We can use a different calculation. The different calculation that we might use is for a force, how much force will take to extend the spring of 225 Newton meters by 0.3 meters, which is obviously what the maximum extension can be. And when we find that out, we end up with a force of 67.75 newtons. And we know 750 newtons is way bigger. Now, 750 newtons would be a person of around 75 kilograms. That's just a adult weight, okay? So the spring, it's not like the spring is really strong and the person sitting on it is huge. It's just the spring is weak. Figure 9 shows a child dropping a stone into water. When the child drops a stone, it passes the child's feet with a velocity of 3.1 meters per second. The child's feet are 6.3 meters above the water. Acceleration is that much. Calculate the velocity of the stone as it hits the water. Interesting. So this is a Suvat equation, as we might say. Suvat. Okay. All of those terms, all of those symbols, you need to know what that means. This is displacement, then U is initial velocity, V is final velocity, A is acceleration, and T is time. Okay, and in this equation, we are asked to find the final velocity. This is what we're trying to find. So we just need an equation that links this final velocity with the terms that we've been given. We've been given the initial velocity, we've been given the acceleration, and we've been given the distance. So we need an equation that links S, U, V, and A. The equation that's in your equation sheet, as well as the one that you have to remember, is V squared minus U squared is equal to 2AS. That has S, U, A, and V, and we just have to find V. Quite simply, we can rewrite this equation as V squared is equal to U squared plus 2AS, because I moved the minus U squared over onto the right hand side when it becomes a positive U squared. Then substitute my numbers in for all of the values that I have. V squared, I don't have, is equal to 3.1 squared plus 2 times acceleration is 9.8 times by 6.3, which is the distance above the water. So once I calculate that, I find that V is equal to the square root of all of those. Using my calculator, that I find that 3.1 squared plus 2 times by 9.8 times by 6.3 gives you an answer of 133. So V is the square root of 133.09, and when I square root that answer, I end up with 11.53 as my 536 as my answer. Now they want it, this is an important thing that I didn't spot before, they want it in two significant figures. The first two significant figures are 1, 1, and then this 5, because it's above 5, basically, you round up the second significant figure, therefore your answer ends up being 12. If you don't put 12 on the answer line, then you'll lose the mark for putting it into significant figures, and then you get 4 marks. Altogether, it's a big mark. When velocity is a vector. Describe the velocity of the stone as it falls through the air. Assume there is no air resistance. As it falls through the air, this is the direction of the fall. Okay, so remember, velocity is a vector means it has a magnitude, which means a size, plus direction. Okay, and what happens to the velocity? Describe the velocity of the stone as it falls through the air. The magnitude of velocity increases, meaning the velocity increases, the direction remains constant. So speed increases, however, it carries on falling towards the ground. 6.3 says, figure 10 shows the stone just after it's entered the water. As the stone moves through the water, the stone slows to a constant velocity. Explain why. So what has happened as the stone moves through the water? It's moving at a high velocity, but it has more drag, because the fluid of a liquid is more dense than a fluid of a gas, so more particles are hitting the stone, therefore the stone is being slowed down because the magnitude of the force upwards, which is the drag, is greater than the magnitude of the weight downwards. So we say drag is larger than weight, larger, greater than weight. So resultant force up, force is upwards, okay, which is opposite to the direction of movement, opposite to velocity direction. So what's going to happen is velocity decreases, so it slows down. But as velocity decreases, drag decreases, because as it slows down, there's less particles hitting the rocks. And finally, drag is equal to weight, which is basically a new terminal velocity. So constant velocity. Now that's a lot of writing. It's a 4 marker, again, a highly marking question. Fantastic kinematics questions. A car contains a device called a black box. Remember, a black box is used to monitor if the driver is being safe. The black box records the velocity and the acceleration of the car. The car was traveling at a constant velocity and the driver then reacted to a hazard, and this shows the velocity time graph for the car. This section, the flat section, is the constant velocity. The gradient section is when it's decelerating, because it's going from a big velocity to a small velocity. So the question is, determine the deceleration of the car. The deceleration, or I'm just going to call it acceleration from now on. Acceleration is the change in velocity over time. Okay, it's the change in velocity over time. The change in velocity is, quite simply, it starts from 26 all the way to 0. So the change in velocity is 26. Time, it goes from 2 seconds to 5. Well, it's in between 5 and 5.5, so it'd be 5.25. So the change in time, of course, is 5.25 minus 2 seconds, which is 3.25 seconds. That's my time. Now, acceleration is change in velocity over time, but you might recognize what I'm about to do from maths. All I'm doing is taking the height of a triangle, dividing it by the base of the triangle, or height of a graph, dividing it by the base of the graph to find the gradient of the graph. So change in velocity, 26 divided by 3.25. 26 divided by 3.25 gets you an answer, a round answer of 8. That's my deceleration. Now, if I took it as a negative acceleration, if I said the change in velocity is that it goes from 26 all the way to 0, so 0 minus 26 is minus 26, then I'll get minus 8. It doesn't matter as long as you follow the same logic throughout. I'm not going to mess around with the minuses for the sake of this question, but it might be that I have to use minuses for another question. So the deceleration is 8. The unit for deceleration or acceleration is meters per second squared, because it's meters per second divided by seconds. It would be meters per second squared. Next question. The driver of the car has a reaction time of 0.75 seconds. Determine the stopping distance of the car. So I'm going to have to write down a statement first that you should all know, that stopping distance is equal to thinking distance plus braking distance. Now, the thinking distance is how far the car travels while the driver is thinking, and the braking distance is how far the car travels while it's braking. So this contains accelerations. This contains, the first one contains just speed, distance, and time. So the car starts off at a velocity of 26 meters per second and goes down to 0. So the change in a velocity, rub that out for a second. We're doing thinking distance, so the car is moving at 26 meters per second and it's moving for 0.75 seconds before the driver decides to press down the brake. Distance is velocity times by time, therefore the distance the car travels is equal to 26 times by 0.75. Therefore the car travels for 19.5 meters in that very short period of time. Okay, then the car decides to brake, and when it brakes, the change in velocity gives you a slowing car. But how do we find the distance traveled by the car that is slowing? Well, we can use this equation: v squared minus u squared is equal to 2as, where s is what we're trying to find, and we know v squared, the final velocity, is 0. We know u squared, the initial velocity, is 26. So this becomes 0. This becomes 26 squared, or negative 26 squared, is equal to 2 times 9.8 times by s, and we know s is equal to negative 26 squared divided by 2 times 9.8. Now it's going to give me a negative value, but it's not. But that doesn't mean it's a negative distance. What we find is the distance when we do this ends up being 42.25 meters. Okay, now there's another way that we can do this. We can do this by remembering that in a velocity time graph, the distance under the graph is the actual distance traveled. So it starts off at 26, goes to 0 in 3.25 seconds. To do that, it's half times base, which is 3.25, times by height, which is 26. 0.5 times by 3.25 times by 26. I mean, I don't know why I'm doing it on the calculator, because it should give me the same answer, which is 42.25. So the blue is my braking distance in blue, and the red is my thinking distance. Stopping distance is thinking distance plus braking distance. All I have to do at the end is 19.5 plus 42.25 gets me the answer, which happens to be 61.75 meters. If the black box records large decelerations, it identifies that the driving may be dangerous. Explain why large decelerations may be dangerous. This is just a question where they are asking you to explore what could happen if the car decelerates too quickly. One of the things that can happen is the brakes could overheat. They could fail also, or fail, or not work. All of those are the explanations. So if the brakes overheat, they could fail or they could not work. Another thing that could happen can lead to loss of control, and if it loses control, why does it lose control? Because loses grip. loses traction, or the greater a deceleration, the greater the force, and large forces could cause injury. So greater force of acceleration or deceleration and could cause injuries. Okay, any one of those statements and explanations or statements and therefores could get you those 2 marks.